Right? You can also define based on the oxidation number or electron loss or gain. Right? So there are different definitions of that. This is the simplest one. The hydrogen addition, if you add oxygen, this is oxidation. Oxygen addition, oxidation, right? Alright. So you can also use other agents over there, like say for example this one or this one. Right? Sodium borohydride, lithium aluminum hydride. Okay? So these are reducing agents. So you can say Al lithium AlS4 and then NaBS4. So these are this over here, right? So these two are reducing agents, right? You can call a hydride agent or reducing agent. So these are reducing agents, right? So you see hydride over there. So this is going to give H minus, right? So both are going to give H minus when they dissociate. So H minus is a nucleophile, right? So H minus, this is nucleophile, like we said in the previous slide. This is a nucleophile. Now it's gonna do the same thing like previous reaction. You have the carbonyl double bond there, so that's the focus you have, right? So what do? You're going to connect nucleophile to the carbonyl carbon, right? So you have that. And then you need proton for the oxygen. So it is in the solvation, so you're going to have the H plus there. So H plus is going to be, you can simply write H plus, or this is H3O plus, right? H3O plus. So proton is going to be from there. You have H going into oxygen, so you have that, right? So OH over there, and then hydrogen over there. Right? So do you see any difference on this if you compare with this one? We have the exact same steps, right? H minus to the carbonyl carbon, H plus to the carbonyl oxygen, right? The difference is you have different source for the H minus. So here simply you have the hydrogen with metal catalyst in it. And the other one, this one, you have the sodium borohydride or lithium aluminum hydride. So these two are the source for H minus. They're the difference, right? You have different reagents. You have the same reactant there. You have the same product there. You have different reagents. Okay? So that's the first question. So if you're going to see step by step, so this is the one. You can see just 2 steps, but if you're going to see the in detail how many carbonyl going to be reduced, so you can see this way. So you have 1, 2, 3, and then 1 on there, 4. You have 4 hydrogens there, right? So 4 hydrides. One molecule of this reagent can give 4 hydrides, one at a time in a sequence. So with one molecule reagent, you can reduce 4 carbonyl molecules. Okay? So that's what it is going over here, but nothing new. the same mechanism. You're going to have minus H minus to the carbonyl carbon, H plus to the carbon oxygen. Okay? So what is the product? Alcohol is the product. Okay? So when you reduce carbonyl, what's going to be the alcohol? Right? Alright, so now next reaction. So this is also reduction. We are continuing with the reduction reaction. Right? So just by seeing the reaction over here, okay, you compare a reactant with the product. If you use the classical definition, oxygen addition or oxygen removal. So what do you see over here? Oxygen lost or oxygen added to have the product.
It's lost.
So you have oxygen over here. So let's number that. 1, 2. 1, 2. So you have the hydrogen over here. There is no oxygen. That's the difference. Right? So loss of oxygen. So what is that? Reduction. Right? So this is continuation of reduction reaction. So now we have this some name for that. So this is based on the special reagent. Okay? So you have the normal carbonyl there. So for this name, this is the special reagent. So this is called hydrazine. That's the name for that. H2N and H2. So you can also write this way. N double bond N, and then you have the H2 over there. Single bond, not double bond. So H and H, right? So this is hydrazine. So that's the molecule. Okay. So now this molecule helps to lose oxygen from carbonyl compound and add hydrogen in it. Right? You have 2 hydrogens over there. So what you're gonna do is these 2 hydrogens, these are from here. You can take it away. So one molecule is going to reduce 2 carbonyl molecules. It has 4 hydrogen total. So 2 hydrogen going to be for 1 carbonyl molecule to give the product. Right? So what is the product? Alkane. Right? So if you just don't see the substitution, so don't see this one. So what do you have? For the carbonyl functional group, you have 2 hydrogens. That means alkyl group, right? Not carbonyl. Now you have alkyl part there. So that's going to be the carbon. So these are other reactants over there. Diol, basic medium, temperature. These are the reaction conditions. But the key reagent over here is hydrazine. Whenever you see the hydrogen there, carbonyl molecule, then you're going to make the reduced product. Take the oxygen out, put the hydrogen in. Right? So how this is going to happen? The mechanism, you can see it this way. Right? So again, nitrogen doesn't stay in the molecule. It's going to go as a byproduct, nitrogen gas. Okay, so this is from the hydrazine, and H, okay, that's the molecule, right? So initially, this molecule is added to the carbonyl molecule, right? So you have the bond there. Instead of oxygen, you have the nitrogen from hydrazine, right? Later, this is going to be out as a gas. those two nitrogen atoms, and then you're going to have the hydrogen added there, right? So two hydrogens from the hydrogen. So that's the mechanism. But remember the final product. So this is the final. You're going to have two hydrogens in place of oxygen. So reduction reaction, right? So this is the third reduction reaction, right? The first one, hydrogen with transition metal catalyst. Number two, with the reducing agent like NaBH4, LiAlS4, so two reducing agents, right? This is the third one with hydrazine. So all three are reducing reaction. So now let's see the opposite of that a little bit. So opposite is going to be the oxidation, right? So what's going to be the product when you oxidize carbonyl compound? So this is going to be a shape. If you remember the rough sequence, so this is what's going to be happening. So you're going to have alcohol, and then you're going to have the carbonyl, and then you're going to have the carboxylic acid. Right? So that's the oxidation sequence. Okay? So oxidation sequence. So this can oxidize to that, this can oxidize to that. Okay? If you go to the reverse order, then what do you call? You're going to say that carboxylic gonna reduce, so now going to be the reduction, right? So carboxylic acid going to be first reduced to carbonyl, and then carbonyl is going to be reduced to alcohol. That's the normal sequence. Okay? So now here we are focusing on the carbonyl. So you're going to have the carbonyl molecule, this one. Okay? Now for the oxidation, you're going to have something that's going to give the oxygen. So you're going to add that oxygen to the carbonyl molecule. You're going to have more oxygen than before. That's why it is oxidation. Okay? So now you need something for the oxygen source. There are so many reactions. Out of them, this is the normal, very frequently used reagent, right? Acid, nitric acid. So it has oxygen in it. That oxygen can be added to the carbonyl molecule. Okay? So now if you see it there, you have all, at the beginning you had double bond O. So this is the one you added there. So you have extra oxygen to the molecule. So the ring is broken. So normally the cyclic carbonyl will be broken. So you're going to have the two ends. So this end is going to be this one and this one. Okay, so this the broken ring into the linear chain. So you have the extra oxygen there. That came from acid, nitric acid. So this is the oxidizing agent, we can call that. So oxidizing agent. Okay. So you're going to have water there. So no matter how concentrated it is, you're going to have some water there. So this is right, 40%, 40%, 20%. So you have water there. You're going to keep that. So the main is nitric acid, so you're going to have the carboxylic acid, right? And other, you can have the oxidizing agent like that, so chromate. You can have the potassium dichromate, potassium chromate, like that, or simply the chromic acid if you have the hydrogen there. So these are all the oxidizing agents. Because you have oxygen there, the oxygen will be used to oxidize, right? So again, for this, your focus is going to be over here. That's the carbonyl functional group, right? So you're going to add oxygen from the oxidizing reagent to the carbonyl carbon. That's the carbon you're going to focus. You're going to add oxygen on that, right? So this is the one. So that oxygen bonded to the carbonyl carbon came from the oxidizing agent. So you have the carbon. This is another one. Or you can say K2Cr2O7. You can also do that. Potassium dichromate. Alright, so next one, you have the another agent over here. Chlorate, that's ClO2. So you can use that too. So you can have the oxygen source there. This is the carbonyl, so now it is aldehyde. Doesn't matter whether they have aldehyde, ketone. Your focus is going to be the carbonyl carbon, right? So now you're going to add oxygen on that carbon. Same thing. You have the different reagent there, but the product is similar, right? In all oxidation, you're going to add oxygen to the carbonyl carbon. That's the common for all. Depending on the substitution, of course, you're going to have different product there, but the key reaction is same for all. So you have that, right? Oxygen added to carbonyl carbon. That's it. So some reduction, some oxidation. These are the reactions. Alright, any questions? All good? Okay. You're going to have, so in principle, you're going to have this. Remember the stoichiometry? So you don't have only one molecule in the reaction, you have millions of molecules, right? So what that means is, for one hydrogen, you're going to have 2 carbonyl reduced. You have billions of molecules there. If you're going to write bicarbonate, you're going to have this way. So you're going to have 2 acid minus. Okay, so you have 2 hydride remaining if you just use one molecule. But you wouldn't care about bicarbonate, so just try to get it. All good? Alright, then we're going to go to the next chapter. So this is going to be a little bit reaction B. So now, so 18 and 19, in particular 19, you're going to have a lot of reactions over there. But 18 is going to be the base for 19. So make sure you know all in chapter 18. So chapter 19 is going to be a little bit easier. Okay. So chapter 18 is going to be carboxylic acid. 19 is going to be the derivative of carboxylic acid. So you're going to have this modification on the carboxylic acid. Let's say, for example, you have C double bond O, OH, and then R. So this chapter is all about this. The preparation of carboxylic acid, reaction of that, some physical properties, how to name that, those things. So this is going to be all of the content of the chapter, right? When you go to chapter 19, what you do is you're going to replace this part by some other groups. Okay? Still you're gonna have R there, you're gonna have CO double bond there, but the OH part is gonna be replaced by so many different groups like amide group, you're gonna have the oxygen containing nucleophile, halide, like Cl minus, Br minus, right? So you're gonna replace by nucleophile because OH is nucleophile. You're gonna replace OH by some other nucleophiles. Okay? So based on that, you're gonna have so many different compounds. You're gonna see the reaction of that. But underlying reaction is gonna be very similar to this one. You're gonna have the very similar steps. Of course, it's gonna be different reaction, different compound. Okay? So let's see it first, and then we're gonna go from there. So now it is obvious, carboxylic acid. So remember, you're gonna always focus on the functional group. So don't care what is the substitution you have there. Okay? Another example, in all these names given over here, your focus is gonna be this one. Your focus is gonna be this one. Gonna be this one, right? Gonna be this one. So other R part, doesn't matter whether they have the ring there, or the branch chain over there, or linear chain over there, doesn't matter. Okay? So the reaction is going to be based on the functional group. So all going to behave same way for the reaction. Doesn't matter how complicated or large molecule it is. Okay? So now, this is carboxylic acid. So this is the functional group, right? You have one carbon oxygen double bond. This is like carbonyl. This is like carbonyl, right? And then other one you have is like alcohol. So in carboxylic functional group, you have two functional groups over there combined, alcohol and carbonyl. So that's why if you see the IR spectra, you're going to see both lines. You're going to have line for the carbon oxygen double bond, carbonyl, and then you're going to have line for the alcohol. You're going to see both, right? So that's the unique nature of the carboxylic acid. You have two functional groups combined there. Carbonyl and alcohol. So make sure both are on the same carbon. So don't be confused with that. If you have these in different carbon, you don't count these as carboxylic acid. So both functional groups are going to be on the same carbon. Alright? So that's the carboxylic acid. So now again, this is carbonyl, this is hydroxyl or alcohol. Take it away. So both combined are going to be carboxyl. Right? Carboxylic acid. Right? So that's the functional group. So now how to name. So the first thing is to name them. So again, naming, you're gonna do the same procedure for all atoms or molecules, whatever you have, right? So alkane, alkene, alcohol, carbonyl, carboxyl, you're gonna have the same basic rule. You're gonna have some small modification on the top, but the underlying rule is gonna be the same, right? So let's say this one, this molecule over here. So your first thing is to find the parent chain, longest possible carbon sequence. Okay? So what's going to be that? So if I go this way, of course, right? This is the continuous sequence of the carbon. You should not have the breaking in a sequence, so it will be continuous. So I have 1 carbon, 2 carbon, 3, 4, 5, 6. I have 6 carbon in the continuous manner, right? So what is going to be the base for that? So hexane, if you just have the 6 carbon atom without any other thing, hydrocarbon is going to be hexane, right? So now you have the functional group there. So you're going to remove E, A and E based on the functional group you have there, right? So now you have 2 functional groups. You have one alkyl halide. You have the halide group there. You have the other carboxylate. So you have 2 groups, right? So now in the parent, which one you're going to include? Or in other words, out of these 2 functional groups, which one going to count as a branch and which one going to count in a parent chain? Okay? So the group with the higher priority going to go to the parent and less priority going to go as a branch. Right? Now you're going to see the table. So you're going to see the carboxylic acid at the top. Right? And you're going to see the halide at the bottom of the table. So the carboxylate is going to have the highest priority of all the functional groups you have. And the alkyl halide is going to have the least priority of all the functional groups you have. Right? That's the reason why you're going to include acid as the parent functional group. Okay? So now how to do that? So you're going to do OIC for the carboxylic acid. Okay? So you're going to take the N out from there and then you're going to write OIC for that. Now hexanoic. Right? And then you're going to add acid after that because it is carboxylic acid. So now the parent part becomes hexanoic acid. Okay? So the parent is fixed. Now, the next thing is you're going to write the branch before that. Right? So now to indicate branch, you're going to number the carbon. So you can either number from the right side or number from the left side. Okay? So you're going to number the carbon in such a way that the parent functional group is going to be 1 if possible, if it is at the end. If not, should be the closest or the least possible number. You're going to give that. Right? So if I start from the left, it's going to be what number? So if I go from the left, the green number, 1, 2, 3, 4, 5, 6. So if I follow the green color over there, my carboxylic acid is going to have the highest number label there, which is not correct. So we're going to go from the right. So the carboxylic carbon is going to be number 1. Okay? So I'm going to go to the red number over there. So 1 is going to be the carboxylic acid. You can write 1 hexanoic acid, but obviously it's going to be obvious if you don't write it. If you want to write it, you can write 1 hexanoic acid or hex 1 oic acid, you can write that. So then, what will be the branch? Number 5, bromine, right? 5 bromo. Right, so 5 bromo, 1 hexanoic acid is going to be the name of that. Right? It's not different. Same rule. We're going to follow that. And the other one, 1, 2, 3. So you're going to count a ring as a substituent. So you don't count the number in the ring when you see the parent. So you can have the propanoic acid, OIC acid again, right? So E gonna be replaced by that. So you have the second example over there, right? So other one, so this is the same example, right? Right? Good. And then if you have a ring, you have slightly different procedure for that. So what carbon number ring you have there? 1, 2, 3, 4, 5, 6, 7, right? So heptane will be the number subscript for that. It is cycloheptane when you have the ring over there. So you're gonna write cycloheptane for that. And then whatever you have the carbon attached, you're gonna call the carboxylic acid for that group alone, right? So the carboxylic acid is, this whole thing is for that. If it is attached to the ring. So this is the rule you're going to follow. So for example, to the other one, you're going to do the same thing, right? So for this whole thing, you're going to call carboxylic acid like before, right? And then you have the ring there. So for this ring, you're going to call cyclopentane. So now you have the substitution there. If you don't have any substitution, this is going to be the name. So now you have substitution. So you have ethyl. So you're going to have ethyl over here. Yes, ethyl. And then you're going to have the methyl, right? Methyl over here. So you have ethyl and methyl. So now you're going to number the carbon in the ring to indicate the position of the substitution, right? So what number ethyl, what number methyl? So you're going to do 1, 2, 3, 4 like that. 1, 2, 3, 4, 5. Right? So the carboxylic carbon gonna take the priority again. So that carbon should be 1 always. So whenever you have the carboxylic acid in the ring, the carbon of the ring that has the carboxylic acid gonna be the number 1 carbon always. Okay? After that, you have two choices: going clockwise or the counterclockwise. Okay? So if I go to counterclockwise, there's the blue number I wrote over there. Or I can also go to the clockwise. So I'm gonna have 1, 2, 3, 4, 5 like that. I have two ways doing that. Right? So now one gonna be right, other gonna be wrong. So that. Right? So now to indicate that, so number 1, you're going to have the least possible number for the branching possible. Remember, that is one of the rules we had in program 1, right? And then, on top of that, if you have the multiple branches over there, you're going to have the priority for these branches in the alphabetical order. Okay? So you have those two on top of that. So now, ethyl is going to come first compared to methyl. So ethyl is going to take more priority than methyl, right? So when you have the numbering, ethyl should have the least possible number than methyl. Okay? So if you do that, if you do the blue, you have the number 3 for ethyl. If you go the other way, the red number 1, number 4 gonna be for the ethyl. So number 3 is more preferred than number 4. Least possible labeling for that carbon, right? That's the reason why the blue is right, red is not right. So again, remember, the carbon of the ring that is connected to the carboxylic acid is going to be the number 1 carbon always. There is no any exception on that. So with that, which way you go in the ring depends on how many branches you have and what is the priority of the branch you have there. Okay, so in this case, S1 has more priority, so you're going to assign the least number possible for ethyl. That's the reason why I go to blue way. Okay. So now I'm going to put everything combined. So 3-ethyl 4-methyl cyclopentane carboxylic acid. Right? So those are. So you're going to see the chiral center, and then you're going to see which way it goes. Right? That's the usual one. Okay. Alright, so now sometimes you can have multiple carboxylic acid, right? So more than one carboxylic group. So for example, you have one group over here, and then you have another group over here. 2 on the same molecule. So if you have that, that's easy, you can call di, tri, tetra, right? So those triplets are going to use that. So you're gonna say di. So if you have tri over here, so no, you don't have tri, right? So if you have 3, you're gonna say tri. If you have 4, you're gonna say tetra, and then 4-8 acid. Okay. So that's how you're gonna do it. So this di over here is 2 carboxylic acid. Right? So similarly, another one, the same 2 carboxylic acid. So you're gonna be di over there. So after 2 or 3 is not very common. So sometimes you're gonna have molecule with 2. Okay. So mostly you're gonna have 1. But sometimes you're gonna see 2, or rarely you're gonna have 3. Alright. So frequently used carboxylic acid in the lab. So these are the names we frequently hear, right? So acetic acid, right? CaCOO, yes. So do you think this is familiar? Vinegar, right? Okay, one left. So this is very familiar, common name. Formic acid, to preserve something, you're going to use that. Formic acid, it is very used one. Benzoic acid, lactic acid. So these are the acids very frequently used, and we call them from the common names. So these are common names over here. So on the top you have, these are common names, and the bottom you have the IUPAC name. So it is so common that the top name is also included in the IUPAC. So it's not, you can use for both common and IUPAC. Right? Very common name. Okay. Alright. So let's do one example. So we're going to name this. So how are you going to name this one? Suppose this is in your test. So how are you going to name that? So first, you're going to find the parent. Okay? So for parent, I'm going to say something like this. I can go to the other carbon, I can have the same length, right? So it doesn't matter whether I'm going to go to the last carbon on the top side or not. So how many carbon you have? 1, 2, 3, 4, 5. So I have 5 carbon. So I'm going to write 10, and then I'm going to take the E out from there. And then I can write OIC, acid. Pentanoic acid. That's the parent. Right? And then, do you have any branch there? You have, right? So you have branch, this, which is methanol. Right? So now I'm going to number the carbon to indicate the branch you have. So carboxylic carbon going to have more priority. So you're going to have the number smallest possible for that carbon, right? I mean for this carbon, carboxylic carbon. So that carbon should have the least possible labeling. So it is N carbon. So I'm going to do 1, 2, 3, 4, 5. Right? So now the bronze metal is on the 4th carbon. So you're going to call 4 metal, and then you're going to have the pentanoic acid. That's how you're going to make it. Right? Good. Alright, so now here you have more, right? So for the second one, how many functional groups you have? You have this one, alcohol. You have Y and E, right? You have oil, alcohol, and then you have carboxylic acid, OIC acid. So you have 3 functional groups there. So again, you're gonna go with the priority. Carboxylic gonna be at the top, and then you're gonna have the Y and E after that somewhere in the middle of the table, and then oil, right? So oil and Y and E are gonna be close, so somewhere in the middle of the table. So for sure, carboxylic is at the top, right? So then, what are you gonna give? So you're going to find the 10 like before. So what are going to be the longest possible 10?
6 carbons.
So that one, right? 1, 2, 3, 4, 5, 6. You have the 6 carbon there. So then you're going to have hexane, right? So you're going to have the hexanoic. No take the same. So that's going to be part of the pattern. So now you have the hydroxy there, you have the Y and E there, right? So for the Y and E, so if you have hexane, single bond, what do you do for the triple bond? You're going to change A and E to Y and E, right? So that is for the triple bond. So you're going to do the same thing. Y over here. Right? So hexanoic acid. So this is for the triple bond you have. And then this is for the carboxylic you have. So now the remaining going to be OH, right? So which carbon do you have for the OH? So remember, carbon 1 going to be the acid, right? So you have 1, 2, 3, 4, 5, 6. So you have these 6 hydroxy, and then, oh, you have methyl too. You have 2 methyl, right? So you have methyl over there. So you have 2 methyl, and then the 4, you have Y and E, this 4 is for that, and then you have the uric acid. Right? It is a little bit harder than the first one, right? Alright.